So in this video, we're going to cover parametric equations. Now, what I'm planning to do in a future video is do a whole review session with practice problems for all the topics that we covered since video number 1. And so I have some problems here. We're going to learn all of this. So eliminating the parameter, the tangent slope. So we're going to learn about the unit tangent, velocity, acceleration, right? This is rarely related to physics. So if you have some prior knowledge of physics, this will really help. Yeah, unit tangent, arc length as well, and chain rule. So you're able to write the velocity vector as something new, which, it's the chain rule, but we're going to talk about it. We're going to learn more about something called a cycloid. And I have talked about this, I'm pretty sure, in a previous video, a point on a rolling wheel. And so all of this is going to be pretty cool. Circular motion physics as well. This is some just extra information that we're just going to learn for fun, because parametric equations are really good for modeling like real world scenarios. That's why it's used in physics. And so right over here, this is a parametric equation. Look at how cool this is. All right, so you can see that we have the x value being equal to t squared, and we have the y value being equal to t to the third. And so on this coordinate plane, we have the x-axis and the y-axis, and this time variable, it seems to be controlling where this point seems to be going, right? You can see that when t is equal to 0, of course, 0 squared is 0, 0 to the third is 0, so we're going to be at the origin. And let's say we're at this point, t is equal to 1, well then 1 squared is just 1, 1 to the third is just 1, so it makes sense that we're at the point 1, 1. And so you can see that both the x and the y value are basically controlled by this one parameter that we have here, aka time. Time is probably the most popular thing for parametric equations because you can model particles moving along the coordinate plane as time progresses. All right. So this is the cool thing about parametric equations. You don't need an explicit kind of relationship between x and y. As long as you know how x is changing over time and y is changing over time, you're still able to model the position of the particle over time. So you can think about the position of the particle, which is usually denoted as r of t, with some sort of like arrow symbol on top. So r of t is going to be equal to, and then there's going to be one function for the x component in this case, and one function for the y component. So we saw how the x component was t squared, and the y component was t to the third. So this is going to be, the first parametric equation that you might have seen before, right? This is going to be the first parametric equation. The x value is changing according to this function. The y value is changing according to this function. All right. So one way to think about this is that this t squared right over here, well, that gives us the x position at any time, right? This tells us how does the x value change with respect to time. And so you can think about this as x of t, right? X of t. What's the x value after a certain time period? Well, this is the function that gives it. On the other hand, you have y of t, right? This right over here would just be y of t, because this tells you as time progresses, well, what's the y value, right? And so ultimately, r of t is going to be composed of some function of x of t, x of t, and then some y of t, function. And if it was in 3 dimensions, then of course you would add a z of t. But the important point to note is that everything in this case is going to be changing with respect to time, okay? Now, an easy way to actually graph out parametric equations without actually having a graphing calculator is just using a table. So let's say that this is going to be where my graph is. The easiest way to do this is just to use a table, right? So you have a table, and one column is going to be for the value of t, the other is going to be for x, and the other is going to be for y. So let's just plug in a bunch of random values of t, and let's see how that changes my x and y value. Okay. So when t is equal to -2, well then this is going to be 4. And then after that, this is going to be -2 to the third, which is -8. If you have -1, -1 squared is 1. And then, well, this is going to be -1 to the third, which is -1. We said how both of these were 0. That's just going to be both 1. And then this is going to be 40. So if we were to graph this out, well, let's see how this would look like. So we said how this would be 4 comma negative 8, right? So this is our first point, right? When t is equal to negative 2, we have 4 comma negative 8. Then we have 1 comma negative 1. Then we have 0 comma 0. Then we have 1 comma 1. And then we have, let's see, 4 comma 8. So 4 comma 8 is going to be right here. And so it looks something like this. All right. And if we go back to the graphing calculator simulation, that looks pretty accurate, right? You see how the t squared, what happens is because our x value has a squared term in it, x can never be negative. So we're kind of restrained to, the positive side for the x-axis. Well, the y value, well, it can be negative. If x was just equal to t, what do you think this would look like? It would just be a cubic function. Because now x can take on any value now, and then y would just be whatever that value is to the third power. In fact, if we have x is equal to t, let me do this in white. If we have x is equal to t, and then we had y is equal to t to the third, this is still a parametric equation. But because x is equal to t, I can substitute in x for t. And so I just get y is equal to x to the third. Okay? And so this is the explicit relationship between x and y. All right? Now, because we originally had x, right, as a function of time and y as a function of time, and we substituted x for t, right? And so notice how we did something called eliminating the parameter. We have eliminated this t right over here to make our relationship a lot simpler. So that's just what eliminating the parameter is. You just solve for, in this case, x in terms of t, which is already solved in this case. But you'll see some examples where it might be a little bit trickier. And so the whole goal of eliminating the parameter is to define this explicit relationship between x and y. Now, as you'll see, sometimes it's actually impossible for us to establish like 100% accurate relationship between x and y, which is why parametric equations are useful. You can still model the position of a particle, right, as it's moving throughout time, but sometimes it might be a little bit trickier to establish a direct relationship between x and y. So that's where this time factor comes in handy, okay? Let's think about what happens if x is sine of t. So if x is sine of t, right? Notice how this is just like a sine function, right? It's rotating. The x value is oscillating between -1 and 1, right? The x value is oscillating between -1 and 1. And as the y value as t gets larger and larger, we start to see bigger and bigger, steps in the y direction. And so you can imagine that this function is oscillating in the x direction, but then it would go up extremely, extremely quickly as t grows bigger. If the y value was cosine of t, whoa, look what we get. We get a circle, and it looks like it's centered at the origin, and it has a radius of 1. If I put a 2 here, whoa, now it's a circle centered at the origin with radius 2 now, right? And so what you can see is that a lot of parametric equations, they might be a little bit hard to visualize. Like if I just put like random tangent, secant, whatever functions in there, it might be really hard to visualize at first. But what is extremely common is, well, the circle, right? So if you have x be equal to r cosine of t, and you let y be equal to r sine of t, well then this gives you the equation of a circle that's centered at the origin with radius r. So that's what we just visualized. All right. Now think about why this works. All right. So this is the same thing as the explicit relationship x squared plus y squared is equal to r squared. Right. These two things are apparently the same thing. So how is that the case? Well, let's substitute everything in here, right? So for x, let's substitute r cosine of t, right? We said how if we're able to define a relationship between x and t and y and t, well then I can still substitute everything back into the original equation, and it still should be equal to r squared, right? So let's do it. So if I substitute in x squared here, I'm just going to get r squared times cosine squared of t. And if I substitute in r sine of t here, I get r squared times sine squared of t. And then all of this is equal to r squared. Notice how I can factor out an r squared from both of these terms. So I'm just going to factor out an r squared from both these terms. Now sine squared theta plus cosine squared theta is equal to 1. So all of this cancels out to be equal to 1, and 1 times r squared is still r squared. So everything checks out here. So because of the Pythagorean trig identity, where sine squared theta plus cosine squared theta is equal to 1, we're able to make this substitution work. And it also makes sense because if you think about x and its position on the unit circle, right? We said how on a unit circle, or you might remember from algebra 2, if you draw a ray right over here and it creates angle theta, the point where the ray intersects the unit circle, you draw a line down, and so the x value would just be equal to cosine of theta, y value would just be equal to sine of theta, right, the height here. And so this relationship is just really, really nice. The unit circle way is a nice way to think about how you can, parameterize the equation of a circle. Now, of course, if we wanted to move the circle around so it's not centered at the origin, of course, we can just add a plus h here and then plus k here. And then so instead of this x squared plus y squared, you could go to r squared. We have x squared minus h and then y squared minus k. But everything is still going to work out just the same, okay? Because at the end of the day, this plus h and this minus h and this plus k and this minus k, they're going to cancel each other out. So ultimately, you're still going to end up with the same result. And so let me show you what I mean. So if I add plus 3 here, just moves it, right? We just shift the circle like, what you would do regularly, right? So same thing. Now, you kind of saw for a tiny flash there that if I put a 1 in for y, notice how this looks like an ellipse. And yes, this is exactly how you parameterize an ellipse. So instead of the two radius having to be equal to each other, right? Instead of the two numbers here being equal to some fixed radius r, well then you can have two different radius. So in this case, the radius along the x direction would just be 2, right? Notice how it is centered at the origin and it goes 2 radius here. And notice how the radius along the y direction is 1 because, well, notice how it's just 1, right? If I put a 5 here, or let's say 4, well then it's just going to stretch it along the y direction. So now the radius along the y direction is 4. If I put a 3 here, it's along 3 radius in the x direction. And then once again, you're able to move it left, down, up, right with a couple of extra plus or minus near the end of the equation. Okay. So instead of, the equation of a circle, you would have the equation of an ellipse. And the equation of an ellipse is going to be x squared. And this is centered at the origin, once again, just to make things simple. But of course, we can easily find out that this generalizes for all ellipses that don't have to be centered at the origin. So you have x squared divided by a squared plus y squared over b squared is equal to 1. And you can think about a squared and b squared as like the respective radius for that specific axis, okay? Now, once again, if the radius in one direction is greater than, the radius in the other direction, there's a couple of names that, or vocab terms that you might come across. So in this case, notice how in the x direction, that's longer than the radius in the y direction. So this radius right over here, the radius of 3, would be called the semi-major axis, while the semi-minor axis would be the small radius here of 1. So for the parameterization of an ellipse, well, you might have guessed it, but x is just going to be equal to whatever the radius in the x direction is. So I'm just going to match up the variables. So it's just going to be a times cosine of theta. And then we can add a plus h, or, if we want to move it around. And then for the y value, well, then it's just going to be b sine theta. And notice how if I square everything, well, then a squared is going to cancel out with a, right? If I substitute x into here, and if I substitute y into here, well, then the b squared is just going to cancel out with this b squared on the bottom. And so ultimately, you just get the Pythagorean trig identity, right? Sine squared plus cosine squared is equal to 1, and so 1 is equal to 1, which is why this works. I mean, eliminating the parameter, it's not too bad. Like if I have x is equal to t to the third, and I have y is equal to t squared, well then, to find out an explicit relationship between x and y and eliminate this parameter t, I can cube root both sides. And so I just get t is equal to the cube root of x. And I just substitute this in here, and I get that y is going to be equal to the cube root of x squared. All right, so just directly substitute it in here. Let's do some other trickier eliminate the parameter problems. You can also have weird ones. Like if I let x be equal to tan x, and I let y be equal to secant of x, well, let's think back to the Pythagorean trig identity, right? So sine squared x plus cosine squared x is equal to 1. And so how would I get tangent? Well, if I want to get tangent, I'll just divide the whole equation by cosine squared x. And so I just get tan squared x plus 1 is equal to secant squared x, right? So if I square both sides, and I square both sides here, well, I just get that x squared plus 1 is going to be equal to y squared, right? Because tangent squared plus 1 is equal to secant squared of x. So y squared minus x squared is equal to 1. Now this might be a little niche, but that is going to be the equation of a hyperbola. So if this is tangent of t and this is secant of t, this is going to be equal to the equation of something called a hyperbola. All right. But it's all about establishing like a relationship. Like sometimes eliminating the parameter doesn't mean that you directly isolate x. Sometimes you can have functions where, specific types of, conic sections. It doesn't have to be a function, but you can have like conic sections, like circles, ellipses, hyperbolas, parabolas, where you might have a square in there, or you might have to square both sides, and that's completely fine. Another one, you can have exponentials in there. Let's do an exponential one. So x is equal to e to the t, and let's say y is equal to e to the negative t. For these ones, for these exponential ones, you usually want to isolate it. For the trig ones, you can usually just use some trig identity. All right, we just take ln of both sides. So I get that t is equal to ln of x, meaning that I can substitute in t right over here. So y is equal to negative e to the negative ln x. Let's pop this negative up in the front, or up in the back here. So this negative 1 right over here. E and ln cancels out. So I just get that y is equal to 1 over x, or x to the negative 1. Okay? We can do another one. Let's say that x is equal to ln of t, and y is equal to t squared. So I can take e to both sides. This cancels out. So I just get that t is equal to e to the x. And so if I substitute in here, I just get that y is going to be equal to e to the x and then squared. So e to the x, or e to the x times e to the x, or just e to the 2x. It's pretty weird if you think about this relationship. Like we said how x is equal to, what, ln of t? So the x value changes logarithmically, while the y value changes quadratically. And so ultimately, the relationship between x and y is an exponential relationship. Okay? So these relationships are connected. Okay? So that's just something to keep in mind. Also, when you're doing this problem, another answer that you could have gotten is x times y is equal to 1, right? And so this just becomes a hyperbola, okay? Right, I solved this equation. I got y is equal to 1 over x, or x times y is equal to 1. Yet the graph of it in my plotter right over here, it looks like this, right? It goes up right over here, and then, it goes out towards infinity. But why does it do that, right? Isn't there supposed to be some negative side as well, right? Can't x be equal to some negative number here? Well, from the start, we said how x is equal to e to the t, meaning that if I put in a negative number for t, well then I'm still going to get a positive x, right? X can only be greater than 0. So that means that for the solution right over here, it's y is equal to 1 over x, given that x is greater than 0. So let's talk about derivatives, specifically derivatives of our position function. So we said how r of t represents a function where the x component of this function is some function of time, and the y component of the position is also another function of time. And so overall, this position function is a parametric equation. Now, what if I wanted to differentiate both sides with respect to time? So I differentiate both sides with respect to time. What am I going to get? Well, the derivative of this r of t right over here, well, it represents, well, think about it. Originally, our r of t represents our position, right? Where is the particle located? But when you differentiate it, you get the velocity function. All right. And so I can say that r prime of t, or another way to put this function right over here, is sometimes you use v for velocity. So v of t is going to be equal to, and in order to differentiate this right over here, well, this is just going to be x prime of t. And the derivative of y of t with respect to time is just going to be y prime of t. So what you would do for problems like these is, if you're asked to find the velocity function, you just differentiate the components normally with respect to time. All right, the derivative of this position function right over here is just going to be equal to, well, the derivative of its components, right? You find out how fast the particle is changing in the x direction, and then how fast the particle is changing in the y direction, okay? And then if you wanted to take a step further and differentiate the velocity function, this is r prime of t, sorry. If you want to take this further, well, then you're just going to get acceleration. And hopefully all of this should be quite familiar to y'all. But if it's not, well, then y'all learned something new. So r double prime of t, if you differentiate this again, you're just going to get some acceleration function, which I'll call a of t. And that's just going to be equal to x double prime of t, comma y double prime of t. Okay, so it's the second derivative of the position function. So think about it, right? If you have some particle path right over here, well, think about what v of t is telling you. V of t gives you the vector of the instantaneous kind of particle motion right over here. So as you go from one position into the next position as time changes, well, you want to find out the slope of this tangent line, right? As you have a change in x and a little change in y given a little change in time, I want to find out essentially, well, the components of the slope of the tangent line, right? And so maybe I'll just do another example to help y'all visualize it better, because if this is a fairly new thing, this is extremely confusing at first, I'm not even gonna lie. But let's say if we're at this point of our, position function, and let's say the particle is going like this. All right, so as time increases, your particle is going from the left to the right. Now for a tiny change in time, if you think about delta t as this approaches 0, right? For a tiny change in time, that's going to cause a tiny change in the x value, right? As your particle goes from one position to the next position. And so that's going to cause some change in x, right? Some dx right over here. And on the other hand, well, it's also a tiny change in time is also going to cause a tiny bump in the height of this function, right? dy. So if this right over here is essentially a tiny change in x, and this right over here is essentially a tiny change in y, well then, if I take the ratio between dy dx, well then that's just going to give me the slope of this tangent line, right? And so you can think about dy dx as, well, if I have a tiny change in tiny change in x, and then a tiny change in y, then if you take the ratio between those two changes, well then that gives you the slope of the tangent line. Another way to view the same thing is that, well, our tiny change in y is caused by a tiny change in time. So this is essentially dy right over here, right? A tiny change in time causes a tiny change in y. Well, we also see how a tiny change in time also causes a tiny change in x, right? So you can view this as a dx right over here. And so ultimately, we see how dy over dx is equal to dy dt divided by dx dt, right? As time changes, our y value is going to change a little bit, our x value is going to change a little bit. And so if we divide essentially the ratios, well, you're just going to get the slope of this tangent line, all right? So when you have a parametric equation problem and it asks you to calculate dy dx, right? If we want to calculate dy dx, right? Well, then you just take dy dt, this y prime of t right over here, and then divide it by this dx dt, x prime of t right over here. So that would be how you would do these problems, right? You find out how does the rate of change of y with respect to time, you find out the rate of change of x with respect to time, and the ratio of those two changes should give you this dy over dx. Now, a non-formal way to memorize this is that these dt's cancel out, right? So we're looking over the same little small time period, and so this isn't, obviously this isn't right and this is not rigorous, but hopefully this does. So here's a practice problem I just stole from Khan Academy because I just felt like it. So look, you're given how x relates to time and y relates to time. So if you want to find out the relationship of how x relates to y, well then differentiate. You want to find dx over dt. So what's the derivative of this with respect to time? That's just going to be 2t. And then the derivative of y with respect to t, well, what's that going to be equal to? That's going to be equal to 2 times e to the t, right? Because e to the x derivative is just e to the x. And so if I divide, this isn't dy dx, this is dy dt. And if I divide these two things, I get 2e to the t divided by 2t. And so this cancels out and just get e to the t over t. So answer choice number C would be correct. All right. So here's another practice problem that I want y'all to work on. So we found dx over dt, and then dy over dt. Well, this is just chain rule. So 1 over 2 radical 3t plus 1, and then multiplied by 3. So there's a 1 there, but multiplied by 3. And then so we want to find dy over dx when t is equal to 1. So first, let's just find dy over dt when t is equal to 1. And let's just find dx over dt when t is equal to 1. And then let's just divide those two and then see what happens. So when t is equal to 1, this looks to be like 3 over 4, right? Because that's just the square root of 4, which is 2, and so 3 over 4. And look at this up here. What is this? This is just going to be 2. So if I take 3 over 4 and I divide it by 2, well, now I'm just going to get 3 over 8. So a very small positive slope. So 3 over 8 would be the answer. Now let's think about why that would make sense graphically. So if you were given a graph, you wanted to justify this, well, I've plotted, this, right? And we're essentially trying to find the slope at this point, right, when t is equal to 1, right? So we're trying to find the derivative, and, this looks to be like, it doesn't look that steep, but still a positive slope. So it looks like 3 over 8 would make a little bit of sense here. So once again, this is just going to be like a little review of what we did, but this is actually something called a vector valued function. Vectored valued function, okay? And the reason why it's called that is because you can view the result of this as a vector, right? So as time changes, you're going to be at different positions. So right over here, right, this is position 1, and then as time changes, right, you're going to be at another position, or you're going to be at this position, right? So you can view as time changes, you're going to get all these vectors that represent the position of where you're currently at, right? And so what you can do is imagine if you have like some sort of curve, right? And let's say that this is the origin, right? And so for a vector here, right? For a vector here, right? Let's say this is vector 1. This is vector v, right? If we move a tiny distance, so if we call this, or actually let's just call this r of t, right? This is the vector valued function after some time period. So after some time, we're going to be at this position, and then let's say that this is the vector valued function after maybe another second has passed. So maybe our initial time period plus a change in time. So t plus delta t, right? So this is our position after some time has passed. Well then, notice how if we consider this to be a vector, right, and this is a vector right over here, well then the change in these two values, right, remember vector subtraction and tip to tail method, right? This right over here would be your change. So this vector right over here would be this vector minus this vector. So I'm just going to do this in blue. This blue vector represents your vector valued function after some time has passed minus that initial vector at that time period. Okay? And you might recognize this pattern from calculus. You really like to divide by the change in time, right? Because this is essentially our change in y. This is our essentially change in x. And then if we let the limit as delta x approaches 0, well then we just have our derivative of r, which is r prime of t, right? And we said how that represents velocity, all right? So this is kind of the formal definition for what we're really doing when we're computing the derivative of a vector valued function. What we're really saying is that, well, between some time period, right? So if we start somewhere and then after some time we move to another position, we're going to create a difference vector between the two spots. And so because this vector valued function can be split up into individual components, it's just going to be how much the x has changed over time, and then you can find out how much the y value changed based on this, right? dy over dt. And so this is the beauty of vector valued functions. So let's think about integrals and how they relate to velocity, okay? Let's say that we were given, somebody was driving 6 miles per hour, okay? Or 6 meters per second, all right? Let's say someone was doing 6 meters per second. And let's say that they were doing this for 5 seconds. And we want to find out their total displacement. Well, 6 meters per second times 5 seconds, well, notice how the seconds unit cancels out. And so you get 30 meters traveled in total. And graphically, you can view this as the area underneath this curve. And so this area underneath the curve represents the total displacement. All right, so if you have some function of velocity and time, and you want to find out the total displacement, find the area underneath the curve, right? Which is the same thing as just multiplying it out, right? Because you can view this as a rectangle, right? 6 and 5, that makes 30. All right. So another way to view this is that, well, in a more, maybe calculus way, you can take a tiny step in time. So let's say that I take a tiny time dt, right? A tiny change in time, and I multiply it by the velocity at that specific point, right? So I multiply this velocity at that specific point. And so I keep doing it, right? I keep stepping dt, and then I find the height, and then I multiply it, right? Because I know that multiplying gives me that displacement. And I keep doing it, right? I keep dividing this into strips. I keep finding the area underneath the curve, and then I'll sum all of this up. So we're just going to add all of these rectangles up. And so this is where, the integral comes in, right? So we can say that the integral of this velocity function with respect to time between, let's say, a and b, that's going to give me my displacement. All right. So I hope that is clear. You can view dt as the base, and you view v of t as the height. And the reason why, you're like, oh, this is such a simple example, right? Like, obviously, you could just multiply and get the answer. Like, why do we have to do all this fancy dt stuff? And the reason why we do this is because not everything in life is straight. Like, you could have a function that looks something like this, right? Some cubic, quartic, crazy polynomial looking function that just goes up and down like this. And now what do you have to do? It's the same idea. You just find the area underneath the curve, and I know that gives me my displacement. A lot of people say that the integral is for the area underneath the curve, and a lot of application it is, but I think a better way to view it, and especially in multivariable calculus, is it's just a summation at the end of the day. You're accumulating small quantities. All right, so that's why this integral looks like S, because S stands for sum. Now, this is a little bit different for a vectored valued function. I mean, the idea is the same, but if you're dealing with a vectored valued function, well then, as a result, you're going to get a velocity vector. So right over here, right, if we think about the derivative, right, so maybe the slope of this tangent line, right, instead of that, well, you're going to get like a vector, right? So instead of just a regular scalar quantity, you're going to get a vector that represents your displacement. And so let's do that. So we want to find out the total displacement for this vector valued function. And so let's do it. So if we take the integral of both sides to get the position vector, right? So, or to accumulate the total displacement, right? So we're just going to get the original position function, right? Because recall that if I differentiate, right? If I differentiate position, I get essentially the velocity, right? But then if I integrate velocity, I'll get back the original position function, right? So this is, if I take the derivative with respect to time, and then if I want to go from velocity back to position, I'll just integrate this with respect to time. Okay. And so let's see. So the integral of 3t is just going to be equal to 3t squared over 2. So you just integrate each component, and then so this would just be 4t to the 4. Okay. And let's just assume that we start at 0, 0. So when time is equal to 0, everything is 0. So we don't have to deal with those constants, okay? Now, let's just substitute everything in here and see our, well, displacement. So if I plug in 0 in for here, I just get 0, right? So my first vector, or my first coordinate that I want to consider is 0, 0. That's actually a vector, so I'm just going to use this. So the first vector I want to consider is 0, 0. And if I plug in 5 into here, I got 25 times 3 is 75. So 75 over 2, comma, and then 5 to the 4th power. Let me just calculate this out. So 5 to the 4th is, I think, 625, but yeah, okay. And so this is at t is equal to 0, and this is at t is equal to 5. And so if I take the difference, right, think about what displacement is, right? Displacement is equal to essentially just your change in position, right? Your change in position. Right? If I move from one place to another place, well then, what is my total displacement, right? So if I integrate velocity to get my position vector, and I essentially just find my change in position because it's bounded, right? Well then, if I take the change in this, I'm just going to get this vector right over here. Right? And so this would be my total displacement. Because this is a vector valued function, well then this displacement right over here, the total displacement is represented as a vector. So if, actually I'm just going to graph it out. So if this is my position parametric functions, right? So this is the f of x of t and this is the y of t, right? If I wanted to find my total displacement, it would just be the vector pointing from the time initially to my final time, right? So it would just be a vector that's pointing between these 2 points because that represents the change in position. And notice how the change in my x-axis is from a value of 0 to 37.5. So that's the change in, that's the displacement in the x direction. And displacement in the y direction is just 0, all the way from 0 to 625. So as you can see, these vector valued functions, if you've seen them before, well, this is just kind of like an extended version of it, all right? So instead of dealing with only one component, now you're dealing with 2 components, and then the total displacement is represented by the vector that connects those 2 points, okay? So you're not just dealing with displacement in one dimension now. You're dealing with displacement in 2 directions now, okay? And of course, if this question was asking us to find out the magnitude of the displacement vector, then just use Pythagorean theorem, right? Think about it. 70 over 2, that's essentially my displacement in the x direction. And then 625, that's my displacement in the y direction. So to find out the magnitude of a vector, once again, you could just use the Pythagorean theorem to solve that. Or this can generalize, right? If this was a velocity vector instead, and you wanted to find out the magnitude of the velocity vector, well, then it's the same concept, right? So sometimes you might be asked like physics quantity, like the magnitude of acceleration vector or magnitude of velocity vector, and then it's just the same idea, right? So imagine if we have a scenario like this. So for, let's say, 2 seconds, right over here, I have a dude, right? I got a dude. And for 2 seconds, so for 2 seconds, what he does is he runs backwards at 5 meters per second. So because he's running backwards, my velocity quantity is going to be negative, right? Because it's a vector quantity and it includes, we're going to associate going to the left as being negative. So this would be associated with a negative 5 meters per second, right? Or 5 meters per second to the left. And then after he does this for 2 seconds, then he just turns around and then he does for 2 seconds. He's going to do 5 meters to the right now. So notice how, because he's going to the right, we usually associate right as being a positive thing. And so this is a positive 5 meters per second for 2 seconds. Now, think about what happened, right? This dude went 5 meters per second to the left and then 5 meters per second to the right for 2 seconds. He's going to end up back at the same position, right? So his change in position, or his displacement, that's going to be equal to 0, right? You go here, you go back, you're at your starting point. And you can visualize this using the area underneath the curve, because we saw how displacement is just the area underneath this velocity curve. And so what do I get? Well, this is sorry, this is right over here a little rectangle, and this right over here also gives us a rectangle. And so let's find the area of these two rectangles and sum it up, shall we, to find the total area underneath the curve. And so this is going to be 2 multiplied by 5, that's negative 10. 2 multiplied by negative 5 is negative 10. And this is 2 multiplied by 5, that's positive 10. And so negative 10 plus 10 gives me a displacement of 0. So essentially, the integral from 6 to 2 of my velocity function with respect to time is going to be equal to 0, meaning that my displacement is going to be 0. However, if we're considering distance, well, how much distance has this person traveled, right? How much distance has this person traveled? And keep in mind that distance is a scalar quantity, meaning that we do not care about direction. So if he's traveling 5 meters per second to the left, in terms of speed perspective, that's still going to be 5 meters per second, positive 5 meters per second, because speed doesn't care about direction. And so ultimately, you travel 5 meters per second for 2 seconds, and then you travel 5 meters per second for 2 seconds. And then so the total area, your total distance that you traveled is going to be 20 meters, right? You've traveled 20 meters from this entire journey. And notice how, well, you might have seen this before, but if you take the absolute value of the velocity function, well, then this negative 10 would just turn into a positive 10. So instead of having negative 10 here, you would have a positive 10. You have a positive 10. And notice how that adds up to 20 as well, 20 meters. And so we can say that if you integrate the absolute value of the velocity function with respect to time, that is going to give you the distance. That gives you the distance, total distance that you traveled. Because distance does not care, distance does not care about direction, right? It only cares about like the total length that you traveled. And so direction doesn't matter. So you're able to throw that absolute value sign in so that moving backwards counts the same as moving forwards. Okay, so let's talk about arc length. So if I have a function here, right, arc length is basically finding out, well, the arc length, right? So if this is A, this is R at point A at some time period. And then let's say this is R at some other time period, R of B, right? This is the position. And specifically, it's a vector valued function. But to reduce, clutter on the screen, I'll just write it at points to be simple. Well, I want to find out the arc length. All right, so I'm tracing out the arc length here. So how do I do it? Now, a good way to view these problems is to break them down into smaller tasks. So notice how as I move across this arc over a certain period of time, right, a very small change in time, notice how I get a tiny change in x dx, and I get a tiny change in y dy. And so if I want to approximate this arc length right over here, right, I want to approximate this arc length, well then this just turns into the Pythagorean theorem. So I get that the arc length is going to be equal to dx squared plus dy squared. and then I take the square root of this. All right. Now for both of these terms, what I'm going to do is I'm going to divide by dt squared. So in parentheses, right over here, I'm going to divide both dx and dy by dt squared, right? So I'm putting everything in parentheses, but whatever I have to do to create this, to make this thing equal, well then, to make this entire equation be equal to each other, well then I have to multiply by dt squared, right? I have to multiply by dt squared in order to keep everything equal. Notice how I can factor out a dt squared, and the square root of dt squared just gives me dt. So all of this is just going to be dx over dt squared plus dy over dt squared multiplied by dt. All right, and this dt is on the outside of this square root. So I'm just going to move everything. And so notice how if I take the integral of this from some bound, so from a to b, right? Sorry, a to b of dx over dt squared, which you can also view as x prime of t squared, and then plus y prime of t squared, and then you square root this, and then you multiply this, you integrate this with respect to dt. Well, then this gives me the arc length for every patch right over here that I have. So for every journey that I make, I can calculate the arc length and sum it all up using the integral.